All right, so now what we're going to do is we're going to use a non-x-intercept point, so anything else besides one of these x-intercepts, to solve for the stretch factor a. Okay, so the stretch factor is that number out in front. So we have, maybe it's a 4 times x plus 3 to the second times x minus 4 cubed times x plus 1 to the fourth or something like that. Okay, and so what we need is to figure out how to get that stretch factor. Okay, so these, we know, they're the intercepts. That's not a problem. Well, what we're going to do is we're going to use some other point and plug that into our formula. So what we're going to have is, at the beginning, we're not going to know that 4. We're going to say, well, that's just a. Okay, and then we're going to plug in some point x comma y, whatever it is, okay? And x, we're going to plug in to the places where x is, and the y, we're going to plug in place of f of x. Then we're going to solve for a. So we're going to take y equals, then we're going to take the number here and square it, and take that number there and cube it, and take that number there and take it to the fourth, and then divide all of the whole right side by whatever that equals when you multiply those together. And whenever we get done, that's what a is going to be, and then we can rewrite our polynomial with that a value, that stretch factor, okay? So how are we going to do this? Well, we're going to write a formula for the polynomial of least degree, identify our zeros and multiplicity. All right, well, let's first identify our zeros. So here it looks like we have a negative 2 comma 0. Here we have a 1 comma 0. And here we have a 3 comma 0. Now what is the multiplicity? Well, it's going straight through each time, so all of them have all multiplicity is equal to 1. Now, what else do we know? Well, we also know this intercept here. It looks like the y-intercept is equal to 0, 3. Okay. Now, the key is sometimes when you want to solve for a, that y-intercept is a good one to have, because if you think about it, if we plug in 0 for x, there's a little less work we have to work on, okay? And so anytime they give you the nicely crossing the y-axis, and you can say, okay, that's 0, 3, that's what I would use. And so our function at the point right now is f of x equals a times, now we have the x plus 2 times the x minus 1, and then times the x minus 3. Okay, so those are what we get. Remember, you set that equal to 0 and you solve and you get the negative 2, so you have to basically change that to a positive 2 to get this, okay? And then we're going to say, okay, now we're going to use this point and plug it in here. So 3 equals a times, well, 0 plus 2 is 2. And then, oops. And then we have 0 minus 1, so it's minus 1. And 0 minus 3 is a minus 3. Well, the negative times the negative, those become positive. So 2 times 3 is 6. So we're going to divide that by 6, and we're going to divide that by 6. So a equals 1/2. Okay. So that gives us the final function, f of x equals 1/2 times x plus 2, x minus 1, x minus 3. And so that would be our actual function that we would use of the least degree. Okay. Now, again, we just had to first find our intercepts, and we also included that y-intercept to make it easier when we plugged it in. And then we just plugged in that y-intercept into our function that we came up with, solve for a, and we could write our function out from there. All right, so let's do another one. Okay. Here we have, it looks like 1, 2, 3, 4 intercepts. So what are they? Well, we have a negative 3, 0, a negative 2, 0, a 3, 0, and a 4, 0. Now, what is the multiplicity? So multiplicity is equal to 1 because it goes straight across, straight across, straight across, straight across. So we have just a multiplicity of 1. So that's nice. Now, what else do we know here? When it's coming down here and coming down here, we know it's going to be an even function, even degree when we get done. So that's something to look at. And when they both come down here, we know that k is going to be less than 0. So that a probably is going to be a negative value. Okay, so that's some things we can look at from our graph. And if we look back over here, We knew it was going to be an odd function, and it was going to be with k being positive. And what do we have? Well, we have a positive k, and we have 1, 2, 3 x's. It's odd, and so that makes sense. So let's go ahead and write that. We know it's going to be odd, and k is going to be greater than 0. So I forgot to write that down, but that's something that we can verify. At that point here, yep, we did get that, and so we're good. So if you say, okay, it's going to be odd and k is less than 0, but you find a is greater than 0, you've either looked at your graph wrong or you've done your a wrong and you need to do something else. So it's always good to kind of double check. And so that's kind of what I was doing here because we have such a different graph, this M-shaped thing. Okay. All right, so what are we going to do? Well, we're going to say, well, f of x equals a times, and now we just plug all those in. X plus 3, x plus 2, x minus 3, x minus 4. Now, do we have the intercept? Well, it kind of looks like it goes through a 0, -3, if you ask me. So I'm going to use that. So that's my y-intercept. And these, again, are all x-intercepts. Okay. All right, and they're all multiplicity 1, so it's 1, 1, 1, 1. And does that make sense? 1, 2, 3, 4 is even. It's even degree, so that part checks. So now let's see if we can get that k being less than 0. So we're going to have -3 equals a times. Now we just put zeros in for all those, so it's going to be 3 times 2 times -3 times -4. Well, negative times negative is positive. 3 times 2 is 6, and 3 times 4 is 12. So 6 times 12 is what? 72. So we're going to divide by 72. And so then a is equal to a -3 over 72. And 3 goes in here to, looks like a -1 over 24. Okay. And so our a is negative. That's good because that's what our k value is there. And so f of x equals a -1 over 24 times x plus 3, x plus 2, x minus 3, x minus 4. And so that is our function of lowest degree for this here example, okay? Now, again, you could go plug it in and check it and see if it looks like that, but, I'm pretty sure we're doing all the work correctly, so we shouldn't have to do that. But you can always also check your calculator, make sure that fits what this shape looks like here as well, okay? All right, so now we're going to do the intermediate value theorem. And so this is something that once we get to a little bit later here in the section, we can use our calculator, and it's going to be using the intermediate value theorem to help us here, okay? So intermediate value theorem, if f is a polynomial function, which was what we're looking at now, then if f of a and f of b have opposite signs, that means there's going to be at least one value c between a and b for which f of c is equal to 0. So if we think about that, what does that mean? So, we're going to have some, I don't know, function that looks like that. And say we have a is here, b is here. And we have to think, does there exist some c, in this case, it's going to be right there, where they have opposite signs? Well, if we keep going all the way down here, this is going to give us a is going to be, give us a value of f of that's going to be some negative, some number. It's going to be negative. And at b, well, this is going to give us some value here, and that's going to be a positive. They have opposite signs, so therefore some number here exists where f of c is equal to 0, okay? And so that's what we're doing. So what we have to do is we have to really choose our points a and b appropriately to help us figure out if there is a 0 between them. So what we want to do is confirm at least one 0 within the interval given, -1 to 1. Okay, so what are we going to do? Well, I'm going to just say, well, what is f of -1? And maybe we can come down here. What is f of 1? Okay, well, I'm going to plug in a -1 here. So -2 times -1 cubed minus -1. Okay, well, here in minus and minus, that becomes plus. Well, when we cube a negative, it's going to stay negative. So it's going to be negative times negative is going to be positive. So it's going to be 2 plus 1, and that's going to give me 3. Okay. Now, hopefully, this is going to become negative, and if it is, then we know that there's going to be a 0 somewhere in that interval. So what do? Well, we plug negative 2 times 1 cubed minus 1, because 1 just plugs in there. And so we have 1 cubed is 1 times negative 2 is negative 2 minus 1, and that gives me a negative 3. Now, those are opposite signs. And so therefore, and so 3 triangles like that means therefore, there is a C between negative 1 and 1. Well, maybe we should put an and instead of a comma there. And 1 for which f of c is equal to 0. Okay, so there's going to be some c in there that f of c gives us a 0. And that's all we have to do. We have to look for opposite signs. What about next one? Oh, we're going to do something a little different here. So here, we're looking at global max and global min. All right, so these are the highest or lowest points of the function when we say global max or global min. They're the highest or lowest, depending on if it's a min or max, okay? Now, at a point A, the f of A is going to be greater than or equal to f of x for all x's, no matter what we do for the global max. And f of a is going to be less than or equal to f of x for all x's to get the global minimum. Now, this only works for even degree polynomial functions, okay? And so being even, it means we're doing something like this. We're going to have global min and global max, because if you think about that, if we have an odd function, we're going to have something like that. We're going to have something like that. Now, is there going to be a global max? No, because it's just kind of up and down and up and down. It's not really going to have a global anything. It's not going to have a min or max, really. It's just going to go off to positive and negative infinity. And so there's never going to be a global min or max. So what about local min and max? So this is a little different. We have a local max and a local min. Now these are the highest or lowest points on the interval around x equals a. Okay, so at some point A, what we're going to see is the local max at A, then f of A is going to be greater than or equal to f of x for x on some interval around A. So, we're going to pick some point around A. So if we have, maybe it goes like this and like that. So we're going to pick some interval around A. So if this is A, we're going to pick some interval around it and say, okay, well, is that going to have in this case, it's going to be a global, that's going to be a local max. This is going to be our global max. This is going to be our local max. Now, since this is here, this is actually going to be a global minimum, okay? But this will be a local maximum, okay? Now, local minimum at A, then f of A is going to be less than or equal to f of x for all x on the interval around the x equals A again. So what do we have here? If we look at this, this one is going to be the lowest of all the lows. So no matter what we do here, this one is going to be called our global minimum, okay? But what about this one? Well, if we look around the interval here to maybe here, what this gives us is going to be a local minimum, okay? And it's around the interval of x equals 3, okay? That's going to be around there. So it's all around that value there. Now, if we look at this one, now it looks like we have higher points instead of lower points. And so this one is going to be our global maximum. And now around the interval here to maybe here, this is going to be our local maximum, okay? Now, we could have, would say, well, what if we wanted to have the A here? this then would be the local max in that area, but it's overall, it's the global max. But if we want it in this area here and say we're only worried about everything kind of to the left, that could be a local max too, but it's also going to be the global max. But if we look at the curve as a whole, then this is going to be our local max, whereas that's going to be our global max. Okay. All right, so let's pause there and we'll come back.